Very good morning, my dear MTech students of IM. Today, I want to discuss summary or rather summary of the nanoscience or nanotechnology, quantum science or nanoscience, same thing. Only the thing is, the thickness of the material is in the order of a nanometer. The basic truth is, from material to material, electron dispersion relation changes. For bulk materials, dispersion relation means E is the electron energy, Kx is the x component of the wave vector K, Ky is the y component of the wave vector K, Kz is the z component of the wave vector K. When three free electrons are moving in wave vector space with constant energy, this is called the dispersion relation. From material to material, this dispersion relation changes, and therefore density of state changes, and therefore 31 electronic, electrical, mechanical, thermal properties will change inevitably. Now, if one direction is quantized, say Kz, as in quantum well, I am going to get 2D dispersion relation. It is 3D. 2D, Kz, Nz pi by dz. Quantum well, all of you know. Therefore, two dimensions of K space are free. Electrons will move in two dimensions. One direction quantized. If again Ky is quantized as in quantum well, the equation says as Kx, Ky, Ny pi by dy together with Nz pi by dz equal to 0. This is the equation of 2D. It is quantum well or inversion layer. But it is MOSFET. It is 1D. Electrons are moving in one direction in K space. This is called nanowire or quantum well wire. Again, that free component K is again quantized. I am going to get E Kx Nx pi by dx, Ky Ny pi by dy, Kz Nz pi by dz. This is called quantum dot QD or 0D, since electron cannot move in any dimension. Now, after this, basic electronic property comes as electron velocity. This I tried to again tell. This part is very clear to you. This I want to tell again. That is electron velocity Vx along x direction. Vx is simply d omega dkx. This is 1 by h bar d dkx, where ky equal to 0 and kz equal to 0. Electron velocity along y 1 by h bar d dky, where kx equal to 0 and kz equal to 0. Similarly, electron velocity along z 1 by h bar d dkz, partial differentiation, where kx equal to 0, ky equal to 0 in the bulk dispersion relation. Therefore, effective mass along x direction is mx h bar square kx dkx d with again ky component and kz component 0. Effective mass m square along y direction is h bar square ky dky d. That means x component and z component 0 together with effective mass along z direction 1 by h bar dkz. I rub it and write it very clearly. 1 by naught. This is mz star h bar square kz dkz t, with the simile of that. Loading is corresponding to three velocities. Three effective masses will be generated, which may be function of energy, function of quantum number, depending on the basic dispersion relation. Second, very important electronic property is, as I often tell and you also know, density of state function DOS. DOS in 3D is nothing but, as I have told you, 2 by 2 pi whole cube dvd, where a unit is 1 by ev meter cube. V is the constant volume of K space. Density of state in 2D is simply 2 GV by 2 pi whole square S1 dADE, where S1 equal to sum over nx equal to 1 to nx max. That is, you are going to get in quantum 1. Then in 1D is 2 GV by pi S2 dkxde, where S2 is simply sum over both nx and ny. And in 0D is, that is quantum box, it is 2 by dx dy dz S3 delta E minus E dash, where delta is the Dirac state function and S3 is the sum of the three quantum number, that is nx, ny and nz. In this case, unit is 1 by ev meter square. In this case, unit is 1 by ev meter. But remember, in that case, unit is, in that case, 0D, unit is 1 by ev meter cube. There are the three cases. Excluding this, there is very important thing known as magnetic quantization. In magnetic quantization, the area of the Landau space, EK space, if I apply a quantized magnetic field B, perpendicular of the magnetic field B in the constant energy K space is quantized in accordance with the formulas given by Landau, where B is the quantizing magnetic field and N is the quantum number 0, 1, 2, 3. In this case, density of state is given by B magnetic field EB by twice pi square h bar sum over n equal to 0 to n equal to max d kzd. But in this case, unit is 1 by v meter. All these I have written. Next comes about very important thing, electron concentration. Electron concentration in 3D, in not 3D, is 2 GV by 2 pi whole cube VEF, volume at Fermi energy. Then in 2D, I better write here for the purpose of remembrance, EF 3D, N0 2D, 2 GV by 2 pi whole square, instead of cube, it will be whole square. This is simply AEF 2D. Again, this is sum 1. Unit is 1 by meter cube, unit is 1 by meter square. For 1D, it is GV twice GV by pi S2, that is, if Kx is free, Kx at EF 1D, unit is 1 by meter. And for 0D, in 0D, that is your quantum dot, 2 GV by dx dy dz S3, sum over the 3, F minus 1 eta, where F naught eta equal to ln 1 plus e to the power eta. Therefore, F minus 1 eta I differentiate, I get 1 by 1 plus e to the power minus eta, together with the fact eta is, in this case, EF0D minus E dash totally quantized energy by KBT Boltzmann constant. That's all. That's the all and end all. Together with, I have to tell you, I have covered quantum well, quantum wire, quantum dot electrostatistics, together with the fact under magnetic field, NB, answer is EB by twice pi square h bar. I give n equal to 0 to n max. Answer comes on Kz, again B for magnetic field. That is EK relation. I put, get the result of X square Kz extract and put V is 4 pi by 3k cube. Area is pi ks square. That's all. Now I go to the second important thing, Einstein relation or diffusivity mobility ratio. It can be derived 1 by E in naught divided by dn naught df. One very important electronic property in all devices, diffusivity to mobility ratio is being used. Diffusivity is disorder, mobility is order. It is called order disorder ratio. Another is 1 by L square spinning length, E square by Fcless, dn naught df. Third is very important, average energy U, that is E Ne Fe d. This Ne is same Fe is Fermi function, which I have derived, we know it, 1 by 1 plus e to the power E minus F over kBt, which you know, that is U, average energy. 1, 2, 3. Fourth is very important, that we can also know and we can also do. Fourth is elastic constants. You know Young's modulus of one type, but in nanoscience there are two types of elastic constants. One is C1, that is minus d naught square by 9, dn naught def, and C2, g naught cube by 27, d2n naught def2. These are all important, very important electronic properties. Electronic heat capacity C is du dt. All these types are, G naught is the deformation potential constant, which is a constant of the system. Deformation potential constant. Therefore, we can find out anything if and only if I can know the concentration. That is, as the relation changes, density of state changes. As density of state changes, N naught changes. Consequently, 31 important electronic, mechanical, thermal property will change. This is one line summary. Excluding this, one very important thing is Brewster mass shift. This is important, and with this I will try to complete everything. Brewster mass shift is very simple. This is EC, this is EV, this is EG, this is AE, this is K, this is F. One hole here will go to the Fermi energy. What is the total energy needed to transfer one hole from the valence band, whose dispersion relation is E equal to h bar square k square by 2 mv square, to the Fermi energy conduction band, whose dispersion relation is E equal to h bar square k square by 2 mc. mc is the effective electron mass at the conduction band. Now you see, this is first it is defined by Motion-Brewstein, and it is the famous Brewstein-Moss shift. Both of them derived in 1954. Shift. This is the last part. We can easily calculate this thing, as because we first rub it. This distance can easily be calculated. This total distance delta equal to this is EF, Fermi energy, plus this is EG, plus this I say K, X. I have to find out the value of X. How come? Its relation is E equal to H bar square K square by 2mv. At E equal to EF, K equal to KF, I replace E by EF and K by KF, H bar square, K square. This is H bar square let us see this energy. This is X. E is nothing but X. X equal to, at that point, E equal to F. Therefore, since F is here, H bar square by 2 mv star into Kf square. E is Ef, K is Kf. Therefore, H bar square Kf square by 2 is nothing but Ef into mc. Therefore, X is equal to Ef into mc star by mv star. I feed back this data here. When I feed back, I get the total result as follows. I rub X now and I write Ef. I write it in a better way. Due to my very bad handwriting, please forgive me. X is simply, I make the box the real answer. What I got now. X is Ef into mc star by mv star. As N0 increases, Ef increases, delta increases. Therefore, if I want to plot delta versus N0, as N0 increases, Ef increases, delta increases. Therefore, my plot will be like this. This was very important Brustine BMS shift. We can discuss a lot. I have only discussed 5 or 6 very important property, 25 important thermal, electronic, mechanical properties are also there. Entropy is extremely important property. Many things can be done. And next is scattering mechanism together with Boltzmann transport equation, BT. This I will discuss later on. That's all for today. Thanks to all of you.